Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous lecture we were discussing multiple linear regression and we concluded our discussion on exhaustive search. So the next approach that we use for variable selection and also for dimension reduction is the partial iterative search. So there are few algorithms under this particular approach that we are going to cover. So let's start our discussion. So partial iterative search, this is computationally cheaper in comparison to the exhaustive search that we do. So in exhaustive search we try out all possible combinations of predictors. So therefore it's more like a brute force approach, and therefore the partial iterative search, which works on different algorithms, it is slightly computationally cheaper. But of course there are some pitfalls, like best subset is not guaranteed, right? So there is always going to be this potential of missing some good sets of predictors. So what we actually get is we produce close to best subset. So that is something that we can say that close to best subsets are definitely we are going to get out of applying partial iterative search. So this particular approach is preferred when we are dealing with large number of predictors, right? Because there the computational time that might be required in exhaustive search might be slightly on the higher side. So therefore we would prefer to apply partial iterative search in those situations. So otherwise, if we are just dealing with a moderate number of predictors or even low number of predictors, their exhaustive search is better, because we get some sort of guarantee of producing the best subset model. So therefore with this between these two approaches, we can say that there is going to be a trade-off between computation cost versus potential of finding best subset. So if we want to minimize the computation time, then probably partial iterative search is the way to go. If we want to if we don't want to compromise with the potential of finding best subset, then probably we should employ the exhaustive search. Now under this partial iterative search approach, we have three algorithms that we are going to discuss. So first one being forward selection. So in the forward selection algorithm, we start with the zero predictors. So we start with the no predictor and we add predictors one by one. So and then as we go along, the main idea that what happens in forward selection is that strength as a single predictor is actually considered in this approach. So if a predictor, because we are adding one by one, and if it is significant, then it would remain in the model. If it's not, then it would be excluded from the model. So therefore for a particular variable to appear in the model, to be in the model in a forward selection algorithm, its strength as a single predictor should be on the higher side. So that also being the limitation of this forward selection approach. So we start with no predictors and then we start adding one by one. So if the predictor is significant, that it will remain there. Then the second approach is backward elimination. So in this particular approach, we start with all the variables and then we start dropping them one by one. So the most insignificant variables are dropped first, and in that order we keep on building the models, and we keep on dropping till we reach the saturation where all the predictors that are present, they are significant. So this particular approach, backward elimination, there is no obvious limitation of this approach, except that the computational time that would be required in this approach would also be slightly on the higher side in comparison to other partial iterative approaches. Now the third one is stepwise regression. So in this also we start with just like forward selection approach. So we start with no predictor and then we add predictors one by one. However, we can consider dropping insignificant ones in this particular approach. So as we move along, so we keep on adding predictors one by one, and if there are some insignificant ones, we can consider at any step whether we would like to drop them. So these are three main approaches So let's understand them a bit more using an exercise. So partial iterative search, first we are going to start with the forward selection approach. So in this, as you can see, the data set that we are going to use is the same, that is used cars data set. So this is preloaded, partitioning is already done, and we are dealing with the number of observation that we have is 75 after excluding all the outliers that are there, and the variables of interest, only 8 variables are there, one being the price, that is outcome variable of interest. So again you can see that we are using this reg subsets function, and the price, and then this formula is specified as price tilde dot, that includes all other predictors in the data set. Now you can see the next important argument data is mentioned as GF train, and then method is forward. So that tells the function that we would like to apply forward selection algorithm. So let's execute this code. Now let's generate the summary of this result, this particular model. Now as we did in the previous lecture, that we would like to count the special character, that is asterisk in this case. So that particular function count special character is already created here. You can see here count special character. So we can use this particular function and count the number of asterisk that are there in this particular matrix for different columns. So this particular result we are going to, as we discussed in the previous lecture, this particular result is going to be used as an index vector for us later on. Now as discussed before, first we will have the number of coefficient and different subset models that we produce, that we generate here. Then the RSS, that is residual sum of square, then CP, malloc CP, then R square followed by adjusted R square, and then we will have the output matrix covering all the variables that are there and whether they are present in that particular model or not. So let's execute this. So we get the output here. As you can see, even in this case, forward selection case, that adjusted R square value starts from 0.48 and it keeps on increasing till a 4 variable model, right? This particular row, 4th row, it keeps on increasing. So in terms of adjusted R square, the result of forward selection and exhaustive search seems to be same. Then after that, after reaching 4 variable model and this highest value, adjusted R square value of 0.72, this adjusted R square value starts decreasing, right? As we discussed that there is going to be a penalty for increase in the number of predictors and with respect to the contribution of information, the amount of information. So 4 variable model is the model that we have to select if we follow the criteria of adjusted R square. If we look at the R square value, this is also very similar to, or is exactly same as what we had in the exhaustive search, 0.49, 0.66, 0.73, and then finally reaching 0.74 and then 0.75. So same result, and the numbers are also same for CP value, though we have with us the results of exhaustive search. So you can see these are the this particular table is the result of exhaustive search, and you can see the same numbers are there. So the output that we have got from forward selection happens to be same for forward selection. So this is just in this particular case the data set that we have and the partitioning that we perform. If we change the partitioning, the results might also change, and also because we are dealing with a small data set, so therefore we might not see much difference between these two approaches. Now if we look at the variables, you can see showroom price, SR price being present in the all 8 models, starting from 1 variable model to 8 variable models, and all of them it is present. Then age is present in 7 of such models, starting from 2 variable models to 8 models. Similarly, fuel type petrol is there, then KM is there, and then comes the owners and other variables that are there. So if we are interested in understanding the coefficient, so let's run this. particular function coefficient, and passing the model argument, we will get this. So you can see the one variable model, the coefficient comes out to be 0.24595. this is the value. So SR price being the only variable. Then we look at the two variable model, we have SR price and age. Then you can see age is negatively related here, and then fuel type petrol and SR price age. So just like in the exhaustive search, so we are getting very same results, the same models also. Then after fuel type petrol SR price, we see the kilometers appearing in there. So it's happening exactly like what happened in the exhaustive search, right? However, as I said, if we change the sample of, or if we change the partitioning, if we increase the sample size, or if we change the partitioning, redo the partitioning, then probably the results will change. Now let's come to our next algorithm, that is backward elimination. So again, for backward elimination as well, we can use the same function as subsets, and you can see the one change that we have done here is in the method argument, where we have specified backward as the algorithm in this case. So let's execute this code, and let's also generate the summary of this output. Now here again we are going to do the same thing, that counting of a special character and the other things remain same. So let's execute this code. Okay, we did not create OM2, so let's compute this and then produce this data frame. Now again, if we look at the results of backward elimination, then also we would see that same numbers are there again. So adjusted R square value again is starting from the same 0.48, 0.64. So the values, these values for all three algorithms, whether exhaustive or forward selection or backwards elimination, what we are seeing is up to 2 decimal points. So there might be some difference, maybe there may be some difference if we look at maybe up to 6 decimal points. So the adjusted R square column, you can see that speaking at 4 variable model, 0.72 is the value. Similarly for R square also, it's peaking at the 5 variable model, 0.75 is the value, and the mellow CPs, the numbers are same, so we will have to select again 3 variable model where the value of CP is 1.73. So in this, so the RSS residual sum of squares number, they are also seem to be same. Let's look at the variables. So you can see again SR price present in all 8 models, and age is present in the 7 models, followed by fuel type petrol present in 6 models, and followed by kilometer km, which is present in 5 models. So if we want to look at the coefficients for different variable models, we can do the same using coefficient function. So let's look at this. Again, you would see that SR price is present in the first model, and then the second model you can look at the coefficient also. Age is again negatively correlated as expected in the 2 variable model. Then in 3 variable model, again we have the fuel entry of fuel type petrol with the negative coefficient, negative regression coefficient, and then you would see in the 4 variable model we see the km as well with the negative regression coefficient here. In the same fashion, the results again seem to be very similar. So let's move to our next algorithm, that is sequential replacement. So for sequential replacement, this is something that we have not discussed. So what happens in sequential replacement is we start with all the variables. We start with all the variables, and from there then we select then we identify the best subsets from there, best subset model that could be there. Then for each of the variable in that subset, for each variable we try different whether that can be replaced by some other variable, right? So in that sense we start out, and then these so in the subset model that is selected, for each variable we'll try out for its replacement, and then again we'll have, for if there are 4 variables in the subset model, then for each variable we'll try out different other variables as a replacement, and therefore we'll get 4 more models, and out of those 4 models we'll again check the which one is performing better. If it happens, then we select the best one, and then we proceed further. The same thing is applied again and again till we are not able to find the best model. So this is what we call sequential replacement algorithm, and the stepwise regression approach would also be very similar to what is being specified as sequential replacement. Some variations might differ with the name also. There are going to be variation depending on the implementation that we follow. So in this case, as you can see, we are again using the reg subset function, and the one difference that we can see is the method sequence replacement SUG has been specified. So let's execute this. Let's run this model. Let's also compute this number of this asterisk in each column of the output matrix. Let's compute this matrix. Now we can see again in the adjusted R square value, again it's peaking at the 4 variable model, and the same numbers are there for I square also. It's peaking at the 5 variable model, and the same numbers are there again for CP also. 3 variable seems to be the more appropriate one, and the same numbers for RSS as well. For the variables also, SR price being presented in all the models, then followed by age, and then fuel temperature and KM. So the results seem to be exactly same. Now we are interested in looking at the coefficient value. Then we can do so using coefficient function, and again as we can see this, again the same results are there. There is no change. SR price, then SR price and age, then fuel type petrol, SR price and age, and then fuel type petrol, SR price, and then entry of kilometer km, and the same fashion the same results we get. Stepwise regression, there is another function that is available to us for stepwise regression, that is called step. So in this case, in this step function, we have to pass on the again we have to pass on the lm function as the first argument. So in the lm function, we would be specifying the formula as usual in the first argument, and then the data. The direction is specified as both, so we can add and remove, so both kind of operation can be performed. If you are interested in finding more about this particular function, you can go into the help section, type step, and choose a so you can see choose a model by AIC in a stepwise algorithm. So you can see different options are there. This particular method would also allow us to run backward, forward, and then both. So as we discussed that the stepwise regression is about, we start just like forward regression, and at each step we can consider dropping off insignificant variables. So that is why the both indicating meaning the same, both indicating the stepwise regression. And the other options, using the same function, we can also build backward and forward as well, which we had just done using reg subsets. So in this particular function, the AIC is used to find out the different subset models. For more information, you can always look at the other arguments that are there. So let's use this function. So let's compute this, and this is the results that you get. So you can see that we start with AIC value of 6.89, and the formula that we start with is price, and then other variables, fuel type, SR price, KM, transmission, owners, and airbag plus age. So you can see all 7 variables are present, and we start with AIC value of 6.89. Now if we look at the possible additions and possible addition or elimination that could be there, you can see that if we eliminate transmission, we would gain we will reach the AIC level of 4.917, and that would be a lower AIC value, and then followed by if we remove airbag, then we'll have this 5.146, and then 5.925, and then the existing model that is represented by none. So none means if we don't drop any variable, then this is what we will have, right? All the variables are there, and so we have three candidate models here, when we drop transmission, when we drop airbag, and when we drop when we transmission followed by this dropping of airbag and owners, these are the options, alternatives that we have. So in the next one, if you see that we have fuel type, SR price, KM plus owners plus airbag and age. So we have three variables. One has been dropped, and you can see the one that has been dropped is the transmission, and that was the first one, right? Because we could achieve a lower AIC value 4.917. So that particular one has been selected, and transmission has been dropped. Now again, from this model also, if we further drop airbag, we would achieve a much lower AIC value of 3.147. If we drop owners, then we reach to 3.939, and then if we don't drop anything, then this is the model that we have at present. So two candidate models seem to be performing better than the present model with respect to the AIC value, AIC criteria. Now if we again drop airbag to get the first model, so you would see that we reach the AIC value of 3.15, and the variables that we have in the model are fuel type, then SR price, then KM, then owners, and then age. So if we look at the options that we have is the owners. If we drop owners, then we'll have the AIC value of 2.113, which is less than the value for the current model 3.15. Then the current model is, as you can see, 3.147, that is 3.15. Then further we can drop kilometer, or we can add airbag. So this step we have already followed. We will reach to the previous models. So probably we'll select the first one and we'll drop the owners, and you will see that we reach this step, AIC value of 2.11, and now the variables that we have is fuel type plus SR price plus KM plus age. So these are the four variables. If you remember the model, the final model that we got using res subsets function that we had, they are also using adjusted R square criterion. The final model that we selected was of 4 variable model having the same variable, right? SR price, KM, age, and fuel type, right? So in this case also, as you can see, the first the current model having 2.11, and there is no other model. You can see the first row, right? Among the options that we have, the first row, none, that is the same model. So no other model can improve this further. So using a different criterion, so we talked about the mallow CP, adjusted R square and R square. Using different criterion like AIC, we also get the same results, and in this case by running stepwise regression. Now as I said that in the results that we are getting here, they are with respect to the sample that we have, very small sample. We are dealing with very small samples, and the small number of observation, and also the partitioning. So as I said, if we change the partitioning, the number of the observation that are randomly selected in the training partition, if they change, the results might also change. If you want to see what will happen if we change the partitioning, we can repeat few of the models that we have just run. So let's change the partitioning again. So again, if we do this partitioning again, so we have regenerated these partitions. So as you can see, regeneration has happened. Now if we look at the model, let's look at the let's go back to the same point variable selection. If we look at the exhaustive search, so once the partitioning has been done, we can rerun this, and you would see that the results that we might get might be slightly different. So we'll have to look at this. You can see now the numbers have completely changed. At least the numbers of these different criteria have changed. You can see different partition. You can see adjusted R square. Now start with 0.48, right? The earlier one was different, right? We have the previous results as well in the output. So if we go back, you can find out previous results. You can see we started with 0.48, then 0.64, then 0.71, 0.64, then 0.71, and then 0.72. Now the results that we have now, you can see that we start with 0.48, then we reach to 0.57, then 0.61. So we don't reach to that 0.72 level, and you see that 4 variable model we reach the peak value of adjusted R square 0.63, and then it remains 0.63 for 5 variable model and 6 variable model, especially if we look at only the 2 decimal point, and then you would see for 7 variable model and 8 variable model the value drops again. So we'll have to select 4 variable model to 6 variable model. We get 3 options in this case. You can see just by changing the partitioning, instead of using the adjusted R square as the criterion, now we have to pick from these 3 models instead of just one in the previous scenario, previous partitioning that we did. If we look at the R square value, that is also there also the results remains to be the same, that 5 variable model having 0.68 value is going to be selected. If we look at the CP value, so those numbers have changed significantly. Now we look at CP value 3 variable model, the value is 4.6, and then the this value we need to compare is 4, and difference is 0.6, right? And we look at the next value, so it will be compared with 5, and the value is this one 3.58, so therefore difference of more than 1. So probably 3 variable model is again going to be selected here in this case as well. But if we look at the variables now, the column for SR price, you would see it's still present, so it is still present, and then age is also present, and followed by KM. Now if you see that KM is present in 5 of the models, and if you see the 5 fuel type petrol, it's present in the 4 in the models. If you go back to the previous results that we have had, it was the fuel type petrol which was present in the 6 of the models, and KM was in the 5 of the models, right, 5 of the 8 models. So that has changed. So fuel, the SR price and age, they are still present in 8 models and 7 models respectively, but KM and fuel type petrol, they have changed their places, right? KM coming into 5 models and fuel type petrol in 4 models. So you can see that once we change the partitioning, the results change, and this is mainly due to the small sample size that we are dealing with. If we had a much larger size, probably it won't change despite partitioning, because we would have more number of observation to learn from, to build our model from, and therefore the results are going to be more robust, right? So with this, the same thing you can apply on other algorithm that we have discussed, that with the change in the partitioning, the results would also change. So with this we'll like to stop here. So this also concludes our discussion on multiple linear regression, right? So in the next session we'll start with KNN. Thank you.